All right, so hello everyone, and thank you very much for attending to this presentation. My name is Alex Martinez, and today I will present our reproducibility paper titled Unmasking Privacy, a reproduction and evaluation study of obfuscation-based perturbation techniques for collaborative filtering, which was done together with my colleagues Mihnea, Tufis, and Ludovico Boratto, all of them present here today. All right, so this is the outline of the presentation, okay? It just follows the standard structure of a scientific publication, so I will not spend much more time in here. You have it. All right, so let me start by giving you a little bit of context, right? So as everyone is aware, recommender systems have become a vital tool in our digitalized world, right? With its applications ranging from social media to video or music sharing platforms. So one of the core technologies of this field, and actually the focus of our study, is collaborative filtering, right? Which generates personalized recommendations based on similarities with other users or items. So the systems that follow this kind of reasoning, they usually show superior performance. However, it is also true that they need to be trained on large amount of personal data, raising significant privacy concerns. And this is true especially nowadays under data protection laws such as GDPR. So in order to mitigate such risks, which could be, for example, a potential attacker trying to infer our personal information, data perturbation techniques are used. In particular, in this work, we focus on data perturbation, okay, which is a popular approach due to its simplicity and also low computational cost. In a very general way, data perturbation tries to alter the original data in order to confuse a potential attacker, okay? In this case, trying to hide the true preferences of the user, which is something that we refer to as data obfuscation. So more in particular, our reproducibility study focuses on the work by Batmatch and Pollard, who proposed 8 privacy-enhancing frameworks. 4 of them were designed to deal with explicit ratings, while the remaining 4 were designed to deal with implicit interactions. And these last 4 are actually the focus of our study, okay, since we consider that this is a more realistic scenario. So despite the theoretical foundations presented by the authors, their work lacks an open source implementation as well as an empirical evaluation. So putting everything together, our main contributions are the implementation of these 4 privacy-enhancing framework. Then we also propose an evaluation procedure to create a fair and comparable environment across REXs. And finally, we run extensive experimentation to assess the impact of these privacy-enhancing frameworks into the performance of the recommender systems. All right, so let us move to the theoretical foundations now. So as I have just mentioned, we assume implicit interactions, okay? Which as usual in this field, they are encoded as 0 or 1 in a user item interaction matrix. So examples of these interactions can be clicks on a website or a movie seen or not seen. But the important thing here is that there are no ratings involved. So in this setting, obfuscation is achieved by flipping the value of these interactions. And this is done based on the combination of 2 variables, a random decision variable R and a threshold value theta. So essentially, all right, and in a very general way, for these values, for these 0s or 1s in the interaction matrix, when R is larger or equal than theta, this will result in flipping that value. Okay, so following this reasoning, and to give a very high-level intuition, lower theta values are associated, so lower theta values will make the flipping more probable, right? Increasing in such a way the privacy levels. So there are different ways of generating these values, okay, which lead to the 4 different privacy-enhancing frameworks. However, first, I will introduce another variable, the group numbers, okay? Essentially, this is a positive integer in which the interactions of every user is split into. So to understand this a little bit better, let's look at this example. So assume that a certain user, okay, has the following interaction history, where 0 means no interaction and 1 means interaction. Assume also that the group numbers equals 2. Then a possible splitting is the one that you can see on the screen, okay? For each group, we will draw the 2 random variables, R and theta, as I have explained before. Then, as you can see, only for group 1, it holds that R is larger or equal than theta. Then we would only flip or obfuscate the interactions within group 1. So again, to give an intuition, all right, and the assumption of the reference paper as well, is that higher group numbers are associated to more privacy levels, okay? Since we are fragmenting more the users, we are adding more variability, which would be harder for a potential attacker to try to recover the original data back, so the true preferences of the user. All right, so we can now start with the 4 different privacy settings. Let us first focus on the threshold value theta. Okay, we can distinguish between fixed and variable response. So a fixed response means that we use the same threshold for all groups and users, okay, and we set that threshold manually. Then a variable response means that a different threshold is used for each group, okay, and we randomly draw this threshold, okay, between 0 and a certain theta max that we also set manually. Again, for the same reasons as before, this setting is associated to more privacy, okay? The variable scenario, we are adding more variability as the name indicates. It is also worth mentioning that the decision variable R is group specific, okay? So we randomly draw this value for each group. Then we also have the masking variable, okay? The motivation behind this is that a potential attacker could try to infer our preferences not only from our positive interactions, but also from our negative ones. Then masking means that we add fake or synthetic interactions, all right? Or what is the same, we convert zeros to ones. On the other hand, no masking means that we do not add these fake interactions, okay? We just hide the true preferences of the user, or what is the same, we convert ones to zeros. All right, so we can now move to our evaluation protocol that we designed. So as I am sure everyone is aware, a standard practice in machine learning involves splitting the original data into train and test set. And this is usually done in a random way. However, in our particular case, we are modifying the original data. We are obfuscating such interactions, right? So we need to pay special attention to this step. In particular, we need to ensure that the test set remains the same across all privacy settings, okay, in order to create a fair environment to compare among them. And besides, we need to ensure that this test set only contains original data, not obfuscated interactions. In such a way, we will be, when we evaluate our recommender, we will be assessing the impact of these privacy settings into the true preferences of the user. So, in order to address these challenges, we propose the following. First of all, our splitting strategy is based on the well-known leave one out procedure, okay, which involves retaining the last interaction of each user for the test set, in our case, according to the timestamp information. Then, the remaining data, not below this test set, this will be our training set. And it is only to this training set where we will apply the obfuscation frameworks. So, in summary, we will be training our recommender system using obfuscated data, okay, different configurations, as I will explain right away, but testing them on the same set across all these different privacy settings. And this set only contains original data. Then finally, we evaluate our recommenders using the top K evaluation procedure, okay? A standard practice as well that involves generating a personalized list of K items for each user. In our case, we set K equal to 10 for all our experiments. All right, so moving now to the experimental setup, we explored a wide variety of configurations, okay, including the 4 privacy settings, including variable group number, and including variable theta values, just as you can see in the table. This results in exactly 200 different configurations. Then we applied each one of these configurations to 2 famous datasets, the Movie Lens 1 million and the Last.fm 1K, which are used for movie and music recommendation respectively. Then we use each one of these obfuscated datasets to train 2 different state-of-the-art recommender systems. Okay, the neural collaborative filtering, which uses deep, fully connected layers to capture nonlinear relationships between users and items, and the light graph convolutional network, or light GCN, which is a graph approach that uses graph convolution to improve the collaborative filtering approach. So putting everything together, this results in 800 different Praxis experiments, for which we measure both the hit ratio and the normalized discounted cumulative gain, or NDCG. All right, so we can now move to our results, right? So due to the short time of the presentation, I will just discuss the results for the Movie Lens dataset, okay? And I will just mention that for the other one, the Last.fm, we obtained the same results. So we present our main findings in the form of heat maps, okay, as you can see in this slide, where the theta value lies on the horizontal axis and the group number lies on the vertical axis. Okay, in this case, the color of the heat maps correspond to the heat ratio score. Again, for the other metric, the NDCG, we can draw analogous conclusions. So the 4 different heat maps correspond to the 4 privacy settings that I explained, okay, combining with or no mask and fixed or variable response. So let us start by looking at these heat maps in a vertical way, okay, which will allow us to inspect the impact of the group numbers into the performance quality. So as you can see, it is hard to identify any pattern vertically, okay, no matter which one of the 4 settings we look at. So this seems to suggest that the group numbers doesn't have a real effect over recommendation quality, and that we are invited to choose higher group numbers, which, as I have mentioned before, they are associated to higher privacy levels. On the other hand, we can also look at these heat maps in a horizontal way, okay, which will allow us to inspect the impact of the threshold value into the performance of the recommender. So just as a reminder, the assumption of the reference paper is that lower theta values will increase the privacy levels, right? But at the same time, since we are obfuscating more data, the performance of the algorithm should decrease. And indeed, as you can see, in the four privacy settings, we observe this, okay, with the color grading changing from left to right, so from worst to better. So in practice, this just means that, as was one of the assumptions, we kind of need to find a balance between the privacy of the users and recommendation quality. Just mention that these results are consistent across recommenders, okay? Here now I present to you the results for the same dataset, the movie lens, but using the 2 recommenders, like GCN and neural collaborative filtering. And as you can see, we obtain the same patterns. Lastly, we also wanted to inspect the correlation between the dataset size and the performance metrics. So since we are adding and removing data, right, we are obfuscating interactions, this is also a variable. Okay, and this is confirmed in the plots in this slide, where we show the dataset size, which is defined as the number of positive interactions, as a function of the theta value. And as you can see, as we increase theta, we also increase the dataset size. So in order to shed more light into this, we computed the Pearson correlation between the dataset size and the performance metrics. And as you can see in the table, we obtain higher correlation values. So from these results and from our experiments, we can only conclude that it is not clear whether the drop in recommendation quality is due to the algorithmic properties of the framework, or it is an indirect result of the dataset size reduction. All right, so just to conclude my presentation, I will just remark that our main contribution is this open source implementation of the 4 privacy enhancing frameworks, which we use to run extensive experimentation. With it, we show that the group number doesn't have a real effect on performance quality. Then we also show that increasing privacy decreases the performance, the accuracy of the recommender, which is related to our third main finding, that the dataset size highly correlates with the performance of the algorithm. Then, regarding future directions, we just mentioned 3 of them. First of all, we would like to design more experiments in order to disentangle the size effect that I have just explained. Then we would also like to develop a framework for privacy attacks, more realistically test the actual effectiveness of these privacy enhancing frameworks. And finally, a more straightforward direction would be to reproduce the same study, but using the 4 frameworks that deal with explicit ratings that we didn't consider in this study. All right, so this was everything. Thank you very much for listening. And if you have any question, I would be more than glad to answer them now.